and welcome to episode number 17 of CS350 Online. I'm your host, as always, Leslie Eiston. On today's episode, we are going to start talking about devices, which are those super important parts of your computer that let you do input, output, and even give you the ability to do preemption. But first, let's talk about the OS of the day. So today's operating system is called OS2. And yes, this sounds like a very familiar named operating system because you'll note that this is a product, again, of Microsoft and IBM. And IBM has had previous operating systems named similarly, primarily OS 360. And it sure sounds a lot like OS 161, the operating system that we use for this course. Now, OS2 was released in 1987, and again, this is a joint offering by Microsoft and IBM. It stands for, quite boringly, Operating System 2, and the reason why IBM developed this particular operating system was to give users an upgrade to DOS, and it was released with their computer known as the PS2, not to be confused with a PlayStation 2 or the PS2 port on the back of your computer. The PS2 was known as the Personal System 2 series of computers from IBM, and they were fairly well known in the late 80s and early 90s. I had a few of them, although much later in their lifespan. They were all broken. So what did OS2 actually offer? So as I said, IBM wanted to give an upgrade to DOS, because if you remember, DOS was a very limited operating system with no protected mode at first, no virtual memory at first, nothing like that. And though it did come later, and especially through Windows, IBM wanted to provide a bit more still. So they wanted DOS with a protected mode, proper protected mode, and they wanted to have virtualization, not just of memory, but of resources as well. And they also wanted to have a desktop GUI so that you didn't have to remember a bunch of random DOS commands to do anything. They wanted a better file system because the file system that's supported by DOS was very limited in the length of file names and the size of files that it could support. So they introduced their own called HPFS. They also wanted to support multitasking and some degrees of concurrency. So they supported in OS2 up to 64 CPUs. So that's pretty cool. And one of their big things that they wanted was to make sure that OS2 was backwards compatible with all of the DOS and Windows applications that were out there. Because if you want a company to adopt your software, especially an operating system, you have to assure them that everything that they have been doing so far will continue to work exactly the way it has before. And if you can't convince them that that's true, then there's no way that they're going to actually use your operating system. And so OS2 was designed to be completely compatible with DOS and Windows applications. Now, OS2 for a while was a pretty big competitor to Windows, especially with businesses, because it offered a more corporate environment, less of a user environment, and it's been used in things like POS devices. But in the end, it did lose to Windows, and many of you have probably never even heard of it, despite the fact it was used throughout the 90s. Interesting story is my high school. We actually had a lot of computer labs, despite not being in the city, and we actually had some OS2 labs. And the student population largely avoided the OS2 labs. And it kind of shows you why OS2 lost to Windows, because the students avoided the OS2 not because they had never heard of it, but because it was impossible to use. If you sat down at the time with a Windows 3.1 machine, and this is right around the OS2 Warp era, and versus OS2 Warp, Windows 3.1 was very intuitive, it was very easy to use, it just kind of worked. Whereas you went into OS2 Warp and you're like, I don't know what I'm doing. I don't know where to look for things, I don't know what's going on. I can show you what OS2 Warp actually looked like. So this is it here. And admittedly, looking at this, 15, 20 years, more than 20 years later, this doesn't actually look that bad. But at the time, Windows 3.1 just felt a little easier to use. And I know I used these OS2 machines a little bit, mostly because it was a computer lab that was always free, and I could have as many computers at the same time as I wanted. That's another story. But most students did prefer the Windows 3.1 labs just because this was a very strange operating system and it didn't quite behave the way they were expecting. But it did work, and it did end up losing, unfortunately. All right. So, with the OS of the day handled, now I would actually like to talk about our new topic, which is devices and I/O. And before we get into the slides, what I want to do is talk about actual devices themselves. Now, devices are something that you're all quite familiar with. For example, you might have a keyboard. So I've got a little tablet here and it's got a little Bluetooth keyboard attached to it. So this is a device. And there are many other kinds of devices that you've seen. You have mice. You can have these lovely tablets for drawing and writing. All of these things are external devices, and all of them are used for things like input or output. There are, of course, things like printers, and, you know, if you've got a little dancing flower that plugs into your USB port on your desk, that's also a device. Now, there are other kinds of devices too. So what I've done here, and you see on the screen, unfortunately it's not very big. And I'm not sure I can get Mac to make it bigger. No, I can't. But this is actually looking at an overview of this computer here. So this is running macOS Catalina, and it tells you all about my MacBook. So it's saying, you know, the year it was made, what processor it has, how much memory I have, and then it lists some devices. So it lists the fact that I have a Radeon Pro, and I also have an Intel graphics card. And both of those things, by the way, are devices. Now, what I want to show you more is that you can actually go into your system view of your computer, and it doesn't matter whether you're using a Mac or whether you're in Windows or Linux, you will find some way of actually opening up a panel that will show you a bunch of different devices. So here I have the graphics information, and it lists all the information about the particular cards. So here I have my graphics card. It's telling you it's this Radeon Pro 560X. It's telling you that it's attached to the PCI Express bus. It's telling you it's using 8 lanes of that bus. It's a parallel bus. It's telling you how much video RAM. It's telling you the device ID. It's telling you information about the vendor. And you'll notice it gives like hex addresses and stuff like this. We'll talk about that in a minute. And then you'll see it tells me information about my monitor. And then I can go into things like my PCI. And it says we don't have any PCI cards. Parallel SCSI, we don't have any of those either. Printers, it knows about my printer in my house, and it'll tell you all the different information about the printer in my house. So aside from just the regular things like your keyboard, there are devices that are actually built into your system. So you've got FireWire. I don't have any FireWire devices. We've got controllers. We've got USB devices. This is the USB bus. We've got information about the Thunderbolt. All of these things are different devices on your system. Now, this actually doesn't list as many of them as you might imagine. But what's interesting is that there's a lot of devices that we don't think about. So it's easy to imagine devices as being things like input and output devices. So things like your keyboard and your mouse and your printer and your monitor. Obvious devices. But the things that we're not thinking about are internal devices like your graphics card. That's a device. Your clock in your computer. Yes, there is actually a clock in your computer, and that is also a device. And it's a very important device. So there are also network interfaces. Each one of those network interface controllers, or NICs as they tend to be called, is a separate device. So if you have a wireless card, that is going to be one NIC, and if you also have a physical Ethernet port, that's a separate network interface controller, so that's another NIC. Each of those things is a device. So sometimes the devices are physical things that you can see, and sometimes they're components that are built into your computer and you can't see. Most devices, however, are going to be either for input or for output. And in order for an operating system and a computer to actually be usable, we actually need these devices, because obviously I can't tell the computer what to do unless I have some way of interacting with it. Now, what's really interesting about all of these devices is that when you say push a key on the keyboard, how do you let the operating system know that, hey, I pushed the any key on my keyboard, can you please handle that? Well, the devices themselves have to have a minimum amount of processing power. So even something like your keyboard here actually has a little bit of circuitry inside to actually control the keyboard, so that it can detect when you've pushed the any key, and it can send an electrical signal to your CPU. Now in this case, it's going over Bluetooth, but it will send a signal to say, hey, I need attention. And that is the interrupt received by your CPU that causes the operating system to run, the kernel, to actually handle that interrupt and say, hey, you push the any key, and here's how we should respond to that. So every device has some small amount of circuitry to actually control what's going on here and to make sure that they can send signals to the CPU, but also receive signals. Because obviously, I mean, this is just a basic keyboard, so this is more of an input device, but something like a monitor, which you can't see here, but I have a bunch of monitors, and a monitor is an output device. So it has some circuitry on board to receive a signal from the computer, and it knows how to process it and so on. So devices need to be able to interact with the kernel, and we are going to interact with the devices. So how do we actually do this? How do I actually receive these interrupts in the operating system? How do I know what to do for a device's interrupt? How do I even talk to this device? Like if I wanted to, let's say I push the any key on this keyboard, how do I in the kernel of the operating system know which key has been pushed? Does the keyboard actually have a different interrupt signal per key, and the operating system has to know based on which interrupt signal was received, which key was pushed? Because that doesn't actually make a lot of sense, because, you know, this keyboard here this is a full keyboard. I mean, it's a teeny full keyboard, but it actually has like a number pad in addition to the letters. And it's even got the F keys at the top. But if you've got like a gaming keyboard, you've probably got 30 other buttons here. So how do you keep the operating system or the kernel up to date with all of these possible interrupts? What if I invent a new piece of hardware that Microsoft or Linux has never seen before? How do I make them understand all these unique interrupt signals? Well, the answer is that's not how we're doing it. So we actually just have an interrupt signal, and it doesn't give away what exactly has happened. Just a piece of hardware needs attention, and we might know what device it came from, but the interrupt itself doesn't tell us anything about which key has been pushed. What's going to happen is when the interrupt gets fired and the interrupt handler in the kernel runs for that device, the kernel then needs to talk to the device, and it actually needs to ask the device, hey, what happened? And the device actually has to be able to respond. So that's what we're going to talk about today, is how does the kernel interact with things like this keyboard here? All right. So we're going to start by talking a little bit about some terminology that you might be familiar with from CS251 and you may not be familiar with. It's not critically important, but we'll just mention it here. Anyways, there's this concept of a bus. And a bus, you can think of it as a wire. It's a big path, a communication road that can be used to connect a bunch of devices to each other. So for example, there is a bus that goes from the CPU to RAM, and there may be other devices actually connected to that main bus that will enable them to also access things like physical memory. So it's a communication pathway. And in fact, when we're referring to the internal bus or the front side bus, that's actually the name of the bus that goes from the CPU to your physical memory, so your RAM. And it's probably one of the fastest, if not the fastest bus in your system. And there are also peripheral buses. Those are buses that go between the different ports on your computer to permit the devices to communicate with each other. And that, of course, will be connected to the CPU so that interrupts from the devices can actually be received by the CPU. Now, an interesting thing about buses that a lot of people don't know is that if you have a bunch of devices connected to a bus and one of those devices sends a signal, every other device on that bus will see that signal. So it's not like a point-to-point kind of thing where if you have 10 devices on a bus and you want to send a signal from device A to device B, it's not that device B is the only one that will receive that. Actually, every device will see everything that goes on that bus, and each device has to have a bit of processing power to know, is this signal going on this bus I'm connected to, is it for me or not? So devices actually have a fair bit of interesting things inside of them to determine if the signal is for them or not. Then we have this thing called a bridge, and a bridge is actually going to connect two different buses. So it kind of makes sense that you might have the front side bus, the memory bus, to actually be connected to the peripheral bus, because presumably we want to be able to copy data from PCI Express devices into RAM. So we do want there to be bridges or connections between some of these different buses. All right. Hardware in a nutshell. So how are we actually then going to be able to communicate with these devices? So first off, if I have pushed truly a key on this keyboard here, and this keyboard raises that interrupt, how does the kernel of the operating system know which key has been pushed? So what's going to need to happen is the device is going to need to be able to store information about what has happened to it. So for example, on this keyboard here, it might make sense to have a buffer in the keyboard itself, an actual buffer, data buffer, that keeps track of the keys that are being pushed. And then the idea is when the kernel receives that interrupt, the kernel needs to be able to talk to the keyboard and read the buffer that's on this actual keyboard and say, hey, what keys were pushed? And we call these data buffers, or these different data storage things that are actually on the devices, we're going to call that device registers. Now, there are three primary types of device registers to know about. There's a status register, and they are typically read. And a status register is going to tell you something about the device. So, for example, if a device has like this keyboard, let's suppose I turn the number lock on. Well, that could be a status register on the keyboard that says numlock is on. So I could have a register just for the numlock. Or it might be something like maybe on your hard drive, maybe there has been a failure to do something, and when I get the interrupt from the device, I need to know, did the operation I asked the disk to do succeed or not? And I'll check the error status register and I'll get an error code out of it. And it will tell me that, hey, this disk read you tried to do failed, and here's the error code. So status registers tells you something about the device itself. All right, then we have a kind of register known as the command register. And a command register is a register that you would typically write to, and the act of writing to a command register would tell the device to do something. So for example, you might imagine if I wanted to write or actually display a pixel on a big monitor, there might be a register where if I write some data to it, the monitor will immediately display that data. Or, for example, let's suppose that you have a printer and if you want the printer to actually do the print job, there will be a command register where the moment you write to it, the printer will start printing. So that's a command register. It's to tell the device to do something. Then we have a register known as a data register, and these actually tend to be a bit bigger than the others. And these are actually used to transfer larger blocks of data to and from the devices. So data tends to be both read and written. And it can be used for like a character buffer from a keyboard or a serial console. You can use it for something like writing a frame of data to your monitor. So data registers are for doing larger data transfers. Now, what's really interesting is when you're talking about a small external device like a keyboard, or in a lot of cases, things like these tablets, they want to make sure that the amount of circuitry that they're putting inside of these is as small and as cheap as possible. So instead of having one separate command register and a separate status register, we'll often see registers being dual purpose. So for example, it's very common to see a register that is both status and command. You read it to know what the device is doing, and you write to it to tell the device to do something. And you'll see command and data and a bunch of different combinations as well. So what I'd like to do then is I'd like to actually show you some specs for some of the virtual devices that we actually have in OS 161. Unfortunately, I can't show you some specs for any actual modern devices because, believe me, the specifications manuals for modern devices can actually be pretty big. I can tell you that about, I think it was 13 years ago, the spec manual for an NVIDIA graphics card was about this big. It's huge. And then NDA you had to sign to access said specification was also that big. I know from experience. All right, so the first device I'd like to show you is actually a very important device, and it's one that we don't typically think of simply because it's not one we can see, and that is the clock device. So every computer has a clock. It's used for keeping time, but as you might recall, we are also going to use the clock device for preemptive concurrency, because we want to have an interrupt occur every so many milliseconds so that we can wrest control away from a runaway thread and force another thread to run. So we have an actual physical clock device on the computer. You can't see it. So we have a clock in OS 161, and our clock has 6 device registers. Now, 2 of them are just plain status registers, and they're actually quite interesting. So we have the current time in seconds and the current time in nanoseconds. And you might be wondering, how do you store this time? What is the current time? Are we storing it as day, month, year, hours, minutes, seconds, fractions of a second? Because that's actually a lot of information. That's not actually how we do it either. So how time is stored in a clock register is as the number of seconds or nanoseconds since the epoch. And the current epoch we are using is midnight of January 1st, 1970. That is time 0. And then time has incremented since then. And that's why if you get the time, if there's time commands in C, it comes out of this weird big integer, and you actually have to convert it into like seconds and so on. It's because the time is measured as seconds or nanoseconds since the epoch. Now this actually raises an interesting point. So if this current time is the number of seconds since the epoch, then, and we're using 4 bytes to store that time, are we going to run out of time? Are we going to run out of space? And the answer is actually yes. So there is something known as the end of Unix time. And what's going to happen for the end of Unix time is it is when we officially overflow the current time register. And this isn't, by the way, the first time this has happened, and I'll talk about that in a minute. But the end of Unix time, when we will actually overflow the 4-byte register for current time since the epoch, it actually happens in both of our lifetimes. It happens on January 19th, 2038, so 18 years from now, at 3:14:07 GMT. And at that exact point in time, every device register that is using 4 bytes to store the current time, as time since the epoch, will be overflowed. So, apparently there are parties scheduled for this. Should be fun, right? And as I said, this isn't the first time we've done something like this. So many of you might have heard of this Y2K thing that happened back when we went from 1999 to 2000. But for those of you who are not really familiar, we used to store the year as 2 digits, just the last 2 digits of the year. So if it was 1983, we would store it as 83. And if it was 1999, we'd store it as 99. So what happens in your computer when you try to store 2000? Because the date would be 00. So does your system interpret that as 1900, or does it understand that, hey, and does that matter? Or will your system be able to handle the fact that it might actually be 2000? And people actually had to go back and change the hardware and how their software worked so that we weren't using just 2 digits for the year. My first computer, by the way, used 2 digits for the year. It didn't matter, though. It really didn't matter. I wasn't doing anything important other than like playing Jaybird and stuff like that. All right, so we've got these registers to store the current time. Then we've got a command register and 2 status and command registers. Now these 3 registers here are actually used for creating countdowns. So you have the status and command register called countdown time. And what you're going to do is when you write to this register, you will write how many microseconds you want the clock to do a countdown for. So if you want it to do 100 microseconds, you would write 100 to this register. And the act of writing that number to the register would actually start a countdown for 100 microseconds. Now, when the countdown finishes, this status and command register here called interrupt is going to indicate that the countdown has completed, and it's going to fire an interrupt, and then it's up to you to actually clear the register to say, hey, clock, I'm aware that you finished your countdown. You can stop now. We don't always need to do this, though. Then there's this one thing. So here's the thing. If we're trying to implement preemptive concurrency, we want to have the clock fire an interrupt every, 40 milliseconds. So do you want, each time the clock fires that interrupt, do you want to have to not just clear this interrupt? Do you also want to have to write the countdown time manually? So do you want to have to tell the clock to restart its countdown every single time it fires that interrupt? Probably not. Realistically, we want the clock to do a countdown for 40 milliseconds and just keep on doing it. Just keep doing it. And we don't want to have to tell you to stop. And so if you want the clock to automatically restart the countdown when it reaches 0, then you will also write to the restart on expiry command register. So what you would do is you would first write to restart on expiry to indicate I want the countdown to restart once it's done. Then you would write your 40 milliseconds, of course converted to microseconds, to the countdown time register. And then what's going to happen is the interrupt still fires, but we don't have to restart manually the countdown. So that's kind of cool. Now there's one last part of the clock device that we can do, and that is, interestingly enough, clock devices in computers actually have a speaker. And in modern computers, you don't really see it, but if you push the back button too many times, in like a terminal, your computer beeps. Well, that's actually your clock beeping. And if you look at an old desktop, you would actually see like a speaker wire with a little mini speaker snaking off the motherboard into the front of the computer. And that little speaker is usually attached actually to the clock. And I know it's kind of weird. And if you write to the speaker command register on the clock, you'll actually cause the speaker to beep. That's kind of fun, right? So this is one example of a device. Now you'll notice I didn't really talk about the offset and size fields here. We will revisit what these are for in a bit. So another really important device in OS 161 and in any operating system is the serial console. And that's the ability to consume characters and, it's the ability to read and write characters. So from this device, we actually only have 3 device registers. And again, this is not actually a device that's like a physical thing so much. So what we're going to have is we have a character buffer, and it is a command and data register. The idea is if you are reading from the character buffer, that means that you are getting the characters that were typed. And if you are writing to the character buffer, you are telling the serial console to output some characters. So the writing to the character buffer issues the command for the device to do something, and reading from it tells us what has been displayed. Then we have 2 status registers here. The first status register is the write IRQ. Remember, IRQ stands for interrupt. So the write IRQ is a status register that is going to tell us if a write is in progress, if a write has completed, and if a write has completed successfully. And the same with the read IRQ. That is a register used to indicate if a read is in progress, if a read has completed, and if there is an error with the read. So we have a question here on Twitch that says, I always feel weird about the Y2K problem. Doesn't the computer store data in binary? Then if we only use 2 bits to store years, shouldn't it overflow at 4, not at 100? It's not 2 bits, it's 2 digits. So we were storing the year as 2 digits. So as like 2 integer digits. That kind of seems weird. We're not saying internally that, so if you were to think of this as a register on the clock, as let's suppose your clock keeps track of the current year, what we're essentially saying is that when we deal with reading and writing the clock, we could only send numbers between 0 and 99. Not so much to say that we're only using like that many bits to store it in the clock. We were probably actually using 32 bits to store it, but all of the control logic only let us read or write 0 through 99. And I'm not so certain, I mean, the hardware played a role here, but a lot of the problem was also the software. The software was designed to only support years being defined as 2 digits, not 2 bits, 2 digits. Yeah. Of course, people had to rewrite their software. All right. So going back to the serial console, so we've got these 3 device registers. Now, here's some interesting things. Let's think about a serial console. If I am writing to the serial console, think of it as I'm writing at bash. And I'm typing I want some characters to appear on the screen. Does it make sense for, as characters are appearing on the screen, for another write of characters to the screen happens at the same time? That doesn't make sense. And it doesn't make sense for 2 writes to happen at the same time because we'd be overwriting the command buffer. So if I am currently writing characters out to the serial console, that means that I'm writing to the character buffer. And if I start a second write, then I would be overwriting the previous command or the command that's currently happening. So what does the device do? Well, most devices actually say that this is completely undefined behavior. What is undefined behavior? It means anything could happen. It means that rockets might launch to the moon. It means that your computer might catch on fire. Anything could happen. The device manufacturer is not specifying what kind of level of misbehavior. So we have to be careful about how we interact with these devices, because the devices, generally speaking, the simpler they are, the less likely that they have any built-in synchronization. Keep that in mind. That's actually why we have these status registers here. It's so that the kernel can keep track of whether writes are in progress or not, and make sure that we're not actually causing race conditions on the device. So that actually brings up an interesting question. How do we actually read and write all of these device registers? How do we talk to the device inside the kernel? It's not actually that hard. We have what's known as a device driver. You can think of it as a small program that is responsible for reading and writing the device registers of a particular device. Now, most device drivers, are a part of the kernel. And they would be a part of the kernel because they need access directly to the hardware. So they should be part of the kernel. But not every device driver is a part of the kernel. There are certainly device drivers that exist in user space. For example, in Linux, many printer drivers exist solely in user land. And that might seem really surprising. But let me tell you how it works, actually. I know this quite well because I have written Linux printer drivers. So I was writing printer drivers for dot matrix printers, so impact printers. And you might be thinking I must have been doing this in like the 80s. No, it was the 2000s. People still use impact printers because they're the only printers that can print carbon copy forms. And I was also writing printer drivers for things like POS devices, which at the time, being young, I thought meant piece of shit device. It actually means point of sale, as I later learned. It's little receipt printers. So I was writing Linux drivers for these. And they were user drivers because this is how they operated. So the impact printer was connected to the computer over the serial port. And what we would do is we created a Ghost Script plugin. Ghost Script is a user program that's used for taking data and like text to data and formatting it as things like PostScript and so on. So we made Ghost Script plugins that take the file you're trying to print, and the Ghost Script plugin converts it to the printer's assembly language. So printers actually speak an assembly language. And if you pay a lot of money for your printer, they'll actually just speak PostScript natively. But most people don't shell out for those kind of printers. So what we would do in GhostScript is essentially assemble your Word file into the printer's assembly. And once we have the printer's assembly, we have this little binary file. We did that purely in user land. And then the serial port in Linux is represented as a file, which is a really cool idea. And so we just write our binary file to dev tty1, which is one of the serial ports, and done. And that entire printer driver exists in user space. So I'm not saying every printer driver lives completely in user space. I'm saying some printer drivers can live in user space. So it is possible for device drivers to actually live in user space, but it is much more common for them to be a part of the kernel. Now, what's interesting is the device drivers are most of them are part of the kernel, but it is a loadable part of the kernel. So in Linux, you have loadable kernel modules, and that is parts of the code where you can load them and they will now execute with kernel privilege. And Windows does this as well, and obviously Mac also. So in Linux, there's actually a way to unload and load manually at the command line. Kernel modules, it's pretty cool. I don't remember the command because I haven't done it in a while. But there is in Windows, there is a directory, and it used to be Win32. And any DLL that was put into that directory became a loadable kernel module. It's kind of neat, right? So we're going to discuss device drivers as being part of the kernel itself. So what does a device driver do? Well, the device driver is going to have to implement synchronization for the device, because most devices don't have synchronization built into themselves. It's not to say they can't, and some do, but the kernel is going to be responsible for handling interrupts with that device, and so it makes sense for the kernel to also handle synchronization. So, for example, for our serial console, we only want one device writing at a time, so we're going to have a binary semaphore for writing to make sure that only one write can happen. So here's one way we can implement our device driver for writing to the serial console. So we're going to P the write semaphore, and that's going to make sure that only one write happens at a time. And then whatever character we want to have written to the serial console, we will simply write it to the device's data register. And now we have to wait, because it doesn't instantaneously just happen. The device has to realize, oh, somebody wrote to my character buffer. And then the device has to say, oh, that means you want to put it on the screen. Okay, let me do that. That takes time. So we can't actually release the semaphore until the device has completed the task we've asked it. So we need to wait until the device completes. And one of the ways that we could do this for the serial console is to poll that write IRQ register. So in a loop, repeatedly read the write IRQ register until it indicates either that the write has completed or that there is an error. And then we can either handle the error and propagate it up the system, or once we've noted that the write has completed, we will clear that register to tell the device, hey, yes, we recognize that the write has completed, and we want to clear this register out because we don't want somebody to come along again and read it and get the status from a previous job. So it's always important to clear these. So we write IRQ register to acknowledge the completion, and then we can finally release that semaphore and another write can happen. Okay, so this is polling. It's busy though. It's actively using the CPU to keep repeatedly asking the device, hey, are you done yet? Are you done yet? Are you done yet? And there are still many devices in your computer right now that actually use polling. For example, USB, polling. Yes, USB uses polling. I'll talk about that in a minute. But what a lot of other devices prefer to do is to take advantage of the fact that there's interrupts in the system. And there's no reason to poll, because when the device is actually done doing its thing, the device will fire an interrupt, and the interrupt handler can handle the completion. So to write the same driver as before, taking advantage of interrupts, this is what we would have. And it now takes two parts instead of a single part. So we have the handler, or the device driver write handler. This is the actual part that initiates contact with the device. We P the semaphore as before, and we write the characters to the data buffer. That's it, we're done in the device driver. Now, in the interrupt handler for the serial device, we know that the device has completed because it fired an interrupt. So we're going to acknowledge to the device that we are aware it completed by writing the write IRQ register, and then we release the semaphore. And this avoids that polling. It lets the CPU do some other computations that might be important elsewhere. So you might be wondering, why doesn't every device do this? Why would something like the USB devices use polling still? So my understanding with USB is that in order to support firing an interrupt, you have to do one of two things. The interrupt either has to go on the signal line with whatever other data you have on, like, the bus, which could potentially corrupt the data that connects that device to the bus. Or you actually have to have the device have an additional line, so an additional connection in which that can actually fire the interrupt unscathed. And when they were creating the USB device, they didn't want to put the interrupt on the existing data lines because they knew it would corrupt whatever was going on. And they didn't want to add any additional lines due to costs and so on and so forth. So they found that polling worked just fine. So USB devices tend to be polled. Now, USB is interesting because there's actually a USB controller device on your system. And I mean, this comes down to architectural specifics, but the USB controller may actually do the polling of the individual USB devices. And then you could imagine that it might be possible, depending on your implementation of the USB controller, you might be able to have it fire the interrupts on behalf of the devices. But there's a lot of implementation-y details there. One of the things you're going to see about devices is there's more than one way to do it. So for device drivers, we can do polling, or we can use interrupts, and there's even devices that might use combinations of both. Now, what we haven't talked about is how do you actually write to a device driver? How do you read from a device driver? Or not a device driver, device register. And there are various techniques for doing this. The truth is, the kernel cannot directly write to whatever registers are sitting on this keyboard. It can't. Because the kernel of the operating system would have to know everything about this device, everything about every electrical connection, and it just isn't. We don't want that. Because that would be not sufficiently abstracted. So here, there are two big ways that a kernel can actually talk to the device registers on a device. And they're port mapped I/O and memory mapped I/O. So port mapped I/O is an older technique. And what it does is there is a separate block of memory, a separate address space that uses fewer bits to address it. And so instead of calling the addresses in this separate memory addresses, we actually call them ports and port numbers. And what we're going to do is each device that uses port mapped I/O will map its device registers to port numbers in this special memory region. And in order to read or write from these ports, we actually use special I/O assembly instructions to do that. Now, they're typically things like in and out. Those are the x86. And so if you do things like out, that might be writing from regular RAM into this special port memory. And what's going to happen is the act of using this instruction and the act of writing to that port, well, the device is listening, and it's listening because it's connected to the bus that is attached to that memory, and it sees that write to that port number, and the device will be like, oh, that port number is me. That's my port number. And so the device can grab the data and take it into itself. Or if it sees a read from the port number, it'll be like, oh, well, that's my status register. I will put that information out there so that we can read and write. So we use port mapped I/O is a special address space. It's a special block of memory with special I/O instructions used to transfer data to and from that special address space. Now, truth, it's very fast, very, very fast, for a few reasons, but one of them is because all of the devices that are connected to this special memory, they're all devices. And so we know that every address we see going over that is going to be for some device. And since every device seems every port number, and they have to determine, is this for me or not, since it's only devices that are connected to this, it's not that many things you have to translate to figure out, is it for you or not? But there's a downside. So one of the downsides is that the port memory is much smaller, so it can only support a very small number of devices. The other downside of using port mapped I/O is that in order to access the data in the ports, you have to use these in and out instructions, which are incredibly limited. So if I wanted to say, add 5 to the value in port 7, I have to copy the value in port 5 into regular RAM, update it in regular RAM, and then copy it back. So I can't actually manipulate directly the memory that is in the ports. It's very limited capabilities to interact with it. So there are downs and there are ups to that. A more modern approach is known as memory mapped I/O. And this idea is, instead of using a separate special memory to connect the devices to, we're going to just, hey, we've got this RAM. We've got gigabytes and gigabytes of RAM. Why don't we take a section of physical memory and use that to map our device registers to? So memory mapped I/O takes a section of RAM, and we actually map the devices to regions in that special section. And it kind of operates in the same way. The devices are going to be connected to the main bus, and the devices will see every address read and write request that goes to RAM, everyone, and they will be looking for addresses that they are mapped to. And when they see an address they are mapped to, they'll be like, that's me, and they will handle whatever needs to be done. So the advantage here is that we have a lot more physical memory, which means that we can support a lot more devices with larger device registers. We also don't need any special instructions to handle this. We can just use our regular LW, SW, what have you. Unfortunately, this is slower. One of the reasons why it's slower is because the devices which are connected to that bus are not just seeing reads and writes to device registers. They're seeing every read and write to physical memory, which means that they have to translate every single one of those addresses coming across that bus to figure out, is this for me or not? And that is a lot of extra work. So you might wonder, what do modern computers use today? They must use memory mapped I/O. Actually, they use both. When it comes to devices, like with the device drivers, polling versus not polling, we still use both. And for port map versus memory mapped I/O, we still use both. OS 161, by the way, it just uses memory mapped I/O. Now, this actually brings me back to talking about virtual memory for OS 161. In particular, let's talk about KSEG1. KSEG1, I told you, was used for accessing devices. So what we're actually saying is that KSEG1 addresses correspond to the region of memory that is mapped to the device registers for those for whatever devices we have. And if you actually look at it, this here is the actual range that is used of KSEG1, this is of course the physical address, for devices. So no other part of KSEG1 for OS 161 is used. And in this very small range, right at the end of the 512 megabytes, we have the memory mappings for devices. There are 32 64 kilobyte slots. These slots are used, each slot is for a device. Now, some devices may take multiple slots, some devices may take just one. But each one of these slots can be used to map a device's registers to. But what do we mean by mapping them to a slot? Well, let's go back to the clock. Where is it here? You'll notice in the specification of the clock's device registers, we've listed an offset and a size. That offset indicates where in the slot that device register is, and the size is how big in bytes that device register is supposed to be. Pretty cool, right? So now you know how KSEG1 is actually used. All right. Now, what if I want to transfer something bigger? For example, maybe I am writing a large file to disk. Is there any other ways that I could handle large data transfers? And the answer is yes. So we have a few different techniques for doing large data transfers. There's program controlled I/O, which is kind of what we've been doing. And then there's direct memory access. So program controlled I/O is the CPU itself is actually responsible for writing the data to the device's buffer. So in this case, what we're saying is the CPU would be grabbing the data from one place in physical memory and copying it to some other place in physical memory. And then the device would pick that up. But the CPU would be busy performing that actual transfer itself. Now, this is very easy to implement, but unfortunately, that means the CPU is occupied during that entire data transfer because it itself is doing the data transfer, which means that the CPU isn't doing anything else. So imagine you're trying to watch a YouTube video while you're trying to, say, read a file from your disk. Unfortunately, YouTube would not get so many cycles because we would be busy doing that read. So YouTube would be not as active. So there's another option here, and this is a common option. This is something that your computer does a lot of, and that is this direct memory access. So what we want to do here is we still need the CPU to initiate this, but we don't want the CPU to do the memory transfer itself. So what we're going to do is we have this direct memory access controller, and what's going to happen is the CPU is going to speak to the device and say, hey device, I want you to copy this amount of data from this address to yourself. And then the CPU goes back about its business, having told the disk what to do. And then the disk, because it's connected to that same bus, is going to then go to RAM directly because it now has the address and size of data to copy. And the disk will copy the amount of data that you told it to from one address in memory to itself. And then the disk, when it's done, will fire an interrupt to say, hey, CPU, I finished. And then the kernel of the operating system will go about its business. Now, that is a very high-level abstracted view of how DMA actually works. But the idea is the CPU is not involved with the actual copying of the data, so the CPU can be used to do something more useful. DMA itself has its own device controller, the DMA controller, which if you're looking in your computer, you might, in the device list, you might actually find information about your DMA controller. And you can also find information about that in your BIOS as well. So that DMA controller is going to have a lot more influence on what is actually happening here, but don't worry about that. We're just talking about this at a very high level. So what does your computer do? Does it do just program controlled I/O or just direct memory access? No, it actually does both again. So for actually communicating with these devices, you actually have 4 options. You have port mapped I/O, you have memory mapped I/O, we can also do program controlled I/O and direct memory access. You have a lot of options for how you communicate with an actual device. All right, so that's kind of been an overview of what devices are, how we talk to devices via the device registers, and what a device driver is. And now I'd actually like to dive a little bit deeper on a specific kind of device that is very important to your everyday life, and that is persistent storage. And what we mean by persistent storage is the memory whatever values are stored in it, when power is lost, the data isn't lost, because your RAM in your physical computer, when it loses power, whatever was in RAM is gone. But on your SSD or your hard drive, when it loses power, the data stays, which is what we want. Because if you're going to go and download, I don't know what movies are coming out. I know. Let's suppose you were to go and download Avatar 2, which is apparently is coming. So you went and you downloaded Avatar 2, and then you shut your computer off, and the next day you turn it back on. You want that movie to still be there. You don't want to have to download another copy of it every time. So persistent storage is very important for a system. And it's actually a really old concept. So persistent storage actually originates back in the 1700s from punched metal cards on a weaving loom. So there's the Jacquard weaving loom, and there's a few predecessors of that, where they realized that humans, if you were trying to weave a pattern in a fabric and the human was responsible for controlling the loom, mistakes were really common, and the pattern wouldn't come out the same each time it was repeated. So they got this idea of having these punched metal cards on a chain. They were tied together, and the idea is that there were these pegs, and as the pegs went through the holes of the punched metal cards, it caused the loom to move to the correct positions to weave the correct pattern. So you could get consistent repetitions of a pattern due to this punched card. So that's kind of the earliest form of a persistent storage, because obviously there's no power involved. But we have also had punched paper cards, punched paper tapes, and those have been used throughout up until the 80s. So it's not a new idea. Now, there's been all kinds of other interesting ways that we've had persistent storage. So I'm going to bring up some pictures here. So we've got this concept of magnetic drums. There it is. So these are magnetic drums. And these are using a magnetic medium inside to store data in terms of orientations of magnetic fields. And we've also done other things with orientations of magnetic fields. So aside from magnetic drums, we've also done what's known as core memory. Core memory is one of my favorites because it looks so neat. And what core memory is a bunch of what looks together these woven wires, and at the intersection points of these wires are these little cylindrical magnets. This, I believe, piece right here can actually store 128 bytes of information, and we can read it and so on. I can post a video to understand how this actually works. So we've been using magnetic field orientations to store binary ones and zeros in various ways, and then of course more recently, sorry, I don't want the tape drive. Tape drive is another one. Magnetic tapes came kind of around the time of core memory and magnetic drums. We moved on to these magnetic tape machines. Interesting story about magnetic tapes is that these have been around since, a very, very long time, and we still use them today. So this is like a cassette tape or a VHS tape, but we still use these. Now, why should this be surprising? Well, first off, what is a magnetic tape? For those of you who haven't seen it, you can think of it as a thin plastic that's been covered in a ferromagnetic material, and we're altering the magnetic field at points on the tape to represent the ones and zeros, and then you have a special reader that can read and alter the magnetic field as required. These magnetic tapes, we still use them today. And in fact, University of Waterloo uses these magnetic tapes every day. They're this big though, not as big as you see in this image on your screen here. Magnetic tapes are cheap. They're very, very cheap for doing archives. And so even though this is a very, very old concept for permanent storage, it's also a very cheap idea that we still use today for permanent storage. So looking at cost per gigabyte, it's cheaper to do magnetic tape. Now, why don't we use magnetic tapes for regular storage anymore? For like day-to-day use? Because as you can imagine, random access of data on a magnetic tape would be very slow, because you would actually have to fast forward or rewind the tape in order to get to the point where your data is actually stored. So it really only makes sense these days to use that for archive. And the film industry is another industry that uses magnetic tapes for archives still. And it's not perfect technology. Magnetic tapes are not without faults. They can only be read or written so many times before the material starts to deteriorate. You've got just radiation from the world can actually cause bit rot, where the bits will start flipping. And so every few years you actually have to make new copies. So you'll go in and you'll make a new copy of things that you had there. Now, industrial magnetic tape is significantly better quality than like a VHS. A VHS, you play it 5 times and it's dead. But the industrial ones are a bit better. So we've got magnetic tapes, and then we kind of expanded that idea to floppies and hard disks. So I want to show you one more image here. Let's put the core memory away. So then we got the idea of, having this tape. Well, can't we do something a little less flimsy, a little more durable? So people came up with the idea of, instead of having a magnetic tape, why don't we have a platter covered in a ferromagnetic material? And with that platter, we'll store the data on the platters by altering its magnetic field at various points, and then we'll have some kind of arm that can actually read it. And this is actually a very early form. We call this a hard drive or a hard disk, because the platters are actually physically hard, as opposed to a floppy disk, I'll show you in a minute, which actually, you can sit it and flop it in the air because it's just a piece of plastic inside. This is actually a very old hard disk though, and you can see each of these little platters there has a read-write head. And yes, those platters, by the way, each of those is 39 inches. So they are very, very big. And yes, I have seen these in person. They're huge. They're absolutely massive. We don't use them that big anymore. All right. So we've evolved from things like these punched cards to magnetic tapes, and then floppies and hard disks are an evolution of the magnetic tapes. You have things like CDs, DVDs, Blu-rays. Those started coming in the 80s, and that is, instead of using magnetic fields to store our information, they're kind of like records, in that we're actually altering the surface of the CD, and instead of having how the needle moves, it's how does the light get reflected off the surface. So we're actually going to read those with a laser. And they've been around since the 80s. I don't really think people use these anymore. I buy Blu-rays for my research, but I don't own any CDs. But nowadays, we don't even use hard disks, really. I mean, we use them for large, cheap storage. We don't use CDs. We use solid-state memory, so our SSDs. That actually goes back to the 70s. So that's a fairly old idea. And now we've got this idea of ReRAM, which is resistive RAM. It's RAM that can actually keep its value when the power is lost. And that's been around since the 2000s. And we'll talk more about that in a bit. So what I'd like to do then is to actually talk more. We're going to focus on hard disks, so platter-based disks. And what I'd like to do is actually tell you about what's inside a hard disk and how they work. So if you were to open up your disk, and please do not open up a hard drive, you will do significant damage to it. What you would see is a bunch of platters, and they are mounted on a spindle. And those platters are actually made of either glass or porcelain, so they're incredibly fragile, and they are coated in that ferromagnetic material. And then you've got this read-write arm, and it's got one of these heads for each platter. And what it does is that head sits just a few microns above the surface of the platter, and it can read and alter that magnetic field while the disc is spinning. So what I'd like to do then is, in these last few minutes, I'd actually like to show you a video of what is inside one of these discs. Now, I've grabbed this video from YouTube, of course. So let's watch a video of a spinning disc.
So here we have a 70 megabyte hard drive. We got 4 platters and 4 heads. We're gonna power this bad boy up and put it on the internet. This is from a time when life was a lot simpler.
So what you're seeing in that video, you've got a spindle of platters, and then for each of those platters, what you were seeing was a read-write head. So data is going to be stored at specific positions on specific platters, and to read or write that data, you're going to have the platter spin, but you're all to the correct position. But you're also going to have the read-write head, and you saw it moving there, move to the correct position as well. So hard disks or mechanical drives, as you can imagine, are quite complicated things because there's a lot of moving pieces and moving parts. And floppy drives, by the way, operate in much the same way. So to end today, I'd like to just show you one more quick video here of how a floppy drive operates, doing something really fun. So what you're going to see in this video is you won't see the internals of the floppy drive spinning, but what you will see is the read-write head moving to the correct position, and moreover, you're going to hear the motors. Now the motors are being recorded and the sound is being amplified. I want to say not that much because these are actually incredibly loud discs. So here we go. All right, I know that was very silly, but how they're able to achieve all those different sounds is by issuing different commands to each of the discs, telling them to read or write from specific parts of each of the discs, and they might be able to alter the speed. And since each device motor actually has its own sound for those various different tasks, you can end up taking a bunch of different drives from a bunch of different manufacturers, and you can end up making songs. And I'll post some other links to Piazza, but if you search for, your favorite movie on floppy drives, you can usually find a version of that. All right, so I'm going to end things for today, and in our next episode, what we're going to continue talking about is how hard disks work. So we're going to look at how data is arranged on the platters of the disks. We're going to look at calculating the costs for reading or writing data from a disk. So how long does it take to find the data? How long does it take to actually read or write the data? And then we're going to compare this to how do SSDs work as well. So that's all in our next episode. So we will see you on Thursday.
Ten nový OS2 Warp je vynikající. Opravdu vynikající.
OS2 Warp?
Ten nový software od IBM. Zrovna jsem o něm četla v časopise. Máte tam opravdový multitasking? Snadný přístup do internetu.
Hrozně ráda bych tu síť vyzkoušel. To je můj beeper.